Good afternoon, everyone. My name is Jingbin Yang, a PhD student from Tongji University. Today, the topic I'm going to talk about is the water absorption release of superabsorbent polymers in fresh cement paste, an NMR study. Well, maybe you found this topic is different from the webinar program, because this work has been finished for a long time. And now I think this title may be better for this work, so I changed it. I'm going to give my presentation by this order. The first section is introduction. We all know that if we want to get a high performance concrete, the water to cement ratio must be low to ensure a compact structure. However, due to the too less water, the autogeneous shrinkage occurs, so chlorine is necessary to compensate water. However, the environmental moisture provided by external chlorine can hardly enter the concrete with compact structure. So, internal chlorine is a novel method to mitigate the shrinkage of concrete. Superabsorbent polymer is a kind of effective internal chlorine agent, but do you know how to use it? Normally, there are two mixing methods for SAPs to be used in concrete. The first is to mix the pre-absorbed SAPs and cement, aggregate, and water. The second is to mix the dry SAPs and cement, then add the mixing water. So the question is, which mixing method for SAPs is better? In this work, we will try to give an answer. The low-field NMR technology was used to monitor the absorption-release behavior of SAPs in the fresh cement paste, and the two mixing methods of SAPs were compared. The effect of pre-absorbed water amount by SAPs and the water to cement ratio of cement paste and the behavior of SAPs were investigated. The next section, I'm going to talk about the pre-absorbed water amount and the behavior of SAPs. You can see there are some NMR results. The bird peaks in the T2 range about 1 to 10 are attributed to the water in the cement paste, and the following small peaks are attributed to SAPs. Even if SAP did not pre-absorb water, some mixing water was absorbed in the SAPs from the fresh paste at 5 minutes after mixing. So with the time with the time increased, the peaks area also increased. This indicates that the SAPs absorbed more water with the time increased until 3 hours. However, when the SAPs pre-absorbed a certain amount of water before mixing, with the hydration time increased, the peaks area decreased. You can see for B and C, 3 hours after mixing, the peaks almost disappeared, and comparing the B and C, the more water pre-absorbed by SAPs, the faster water is released into paste. Okay, next we will focus on the second mixing method and discuss the water to cement ratio. To achieve a better internal curing, SAPs with water content sometimes has to be adjusted. However, the result above show that changing SAP's water content by pre-absorbing a certain amount of water might not be an effective method because the water pre-absorbed by SAPs before mixing would release into the paste after mixing. So, is there any other method? Can we control the SAP's water content by changing the water to cement ratio of the cement paste? When the water to cement ratio of the paste was 0.4, SAP's peak at 5 minutes after mixing could be observed, and this peak area was higher than that of the paste with a cement ratio of 0.3, and then the SAPs continued to absorb the water until the peak area slowly decreased after 1 hour, and the peak at each time was higher than that of the paste with a cement ratio of 0.3. Which indicates that increasing the water to cement ratio of the paste from 0.3 to 0.4 did increase the SAP's water content. However, Figure C shows that when the water to cement ratio was further increased to 0.5, no peaks of SAPs could be observed at other times except for a tiny peak that occurred at 5 minutes after mixing, which indicates that SAP's water absorption from the paste was inhibited at this water to cement ratio. So, what happened when we changed the water to cement ratio? This is the SAP result of the pore solutions. We can see that when we increase the water to cement ratio from 0.3 to 0.4, the primary ions, sodium and calcium, both decrease, so the water absorption of SAPs increased. However, when the water to cement ratio further increased, the concentration of calcium increased a lot, and the calcium can combine with SAP structure and increase the cross-linking degree of SAPs, so the water absorption was inhibited. Okay, finally, it's the last session conclusions. Do you remember the question that I mentioned in introduction session? Which mixing method for SAPs as an internal curing agent is better? I think now we can answer that. Obviously, the dry SAPs mixed with cement is better than pre-absorbed SAPs. However, if we choose these dry SAPs to mix with cement, we need to pay attention to the water to cement ratio of paste, because a high water to cement ratio may also promote the dissolution of calcium. Okay, that's all my presentation. Welcome to discuss with me by email. Thank you for your attention.